Hello students, in this video we'll solve a related rate problem with a hourglass. Suppose that we have an hourglass, which is a cone, like this. My hourglass, it's like this. And there is some sand in the top of the hourglass. And let's say that this hourglass has a diameter of 6 inches, and the top of one of these cones is also 6 inches. And so there's some sand in this hourglass over here. And what's the sand doing? So the sand in this hourglass is trickling down and draining over here into this bottom part of the hourglass. That's what the sand is doing. And so we'll recall some properties about cones, right? So for cones, we know that the volume of a cone is 1/3 pi r squared h. That's the formula for volume of a cone. And so let's suppose, so here's the step of the problem. Let's suppose that sand is draining and the volume is decreasing on the top. Is decreasing at a rate of 10, let's say 10 cubic inches cubed, of course, per minute, 10 inches cubed per minute. When the height over here, so that's the height level of the cone, and of course this will be the radius of that, so that's the radius over here. Radius and height. When h is equal to, let's say, when h is equal to 5. Okay? What I'd like to do is I'd like to find how fast is the radius, how fast is the height changing, right? So how fast is the height changing? Okay. So I have a formula for I know how the volume is going to change, but I have an R and an H in this problem, right? I only want what? I want to find out how fast the height is changing. So I want to have only H's in my answer. So our goal is to have only H's in the answer. So I need only H's in the volume formula. Okay, and so here's where a similar triangle saves the day. If the top radius is 3, and so let's look at these triangles over here. Those two triangles, so the top triangle over here, that's a radius of 3, goes straight down to the base of the cone. So that's what my cone looks like. And the height over here is 6. And then when we're at a height of h, we have this triangle over here. So that's my radius over there, and that corresponds to what? This height over here of a height of h. So these two triangles, this little right triangle over here, and this big right triangle over here are similar to each other. So what does that say? That says that r over 3, by similar triangles, has to be what? Has to be h over 6, right? So in other words, r is what? R is h over 2. So now I can take that h over 2 formula and plug it into my volume formula. So my volume is really what? My volume is really 1/3 pi times r squared, but r squared is h over 2 by the configuration of this cone, h squared over 2 times h. So let's tidy this up a little bit. This is going to be a 1/3 pi, and then I have a 4 in the denominator over here, so times 1/4, and then h what? H cubed. So that's a total of what? That's a total of pi over 12 times h cubed. Good, now I can take the derivative. So take the derivative both sides. So dv dt is what? Bring that 3 down, it's going to be a pi over 12 times 3h squared times dh dt by implicit differentiation. Okay? So the 3 and the 12 are going to turn to a 4. And I have the h is equal to 5, so I'm going to plug in h equals 5 over here. So I know now that negative 10, because it's decreasing, negative 10 is equal to what? Is equal to pi over 4. And then h squared is going to be what? 25 times what? Times dh dt. Okay, so I'm going to multiply both sides. I'm going to have dh dt. Therefore, by solving for dh dt, will be what? Well, I'm going to throw the 4 over there, so I'm going to have a negative 40, divide by 25 pi pi is dh dt. And of course, you can cancel some of these things out. That's going to be an 8 over 5, so that's going to be negative 8 over 5 pi. And of course, what are the units of this thing? This is going to be an inch per minute. So an inch per minute. And that's how fast h is decreasing when h is equal to 5. Thank you very much.